In this video, we're going to explain what a manifold with boundary is and a new way to define a manifold in preparation for studying differential forms on manifolds and integration on manifolds. So let's just recall the definition of a manifold. A subset of Rn, or Rm, sorry, is a smooth n-dimensional manifold if every point in M is contained in some coordinate chart. So in an open set, so U is a subset of Rm, it's open in the larger space. And there's also a diffeomorphism phi from U to V, which is another subset of Rm. So diffeomorphism is a bijective smooth map with a smooth inverse, such that phi of U intersect M. I'll actually put this on another line, such that phi of U intersect M is equal to V intersect yn plus 1 equals 0 equals, etc., all the way out to ym equals 0. So basically the Rn subset of Rm where the last m minus n coordinates are 0. And then we say that U phi is a coordinate chart, and the collection of all coordinate charts is called an atlas. So basically it's like an atlas, like a regular atlas for the globe, right? It's every U is like the page, or it's the piece of the globe that's covered by a page of your atlas, and then the atlas actually maps that chunk of the globe to the flat page where the last coordinate, which would be the z coordinate in this case because we have 3 dimensions, is 0. Okay, so conversely, especially when computing integrals, it's helpful to characterize manifolds using the coordinates. So using maps that go from Rm back to, or Rn back to the manifold. So there's a theorem that's in Spivak, theorem 5.2, that says equivalently, M is a manifold precisely when there is an open set U in Rm containing P, an open set W in Rn, and a one-to-one differentiable map, which I'm going to call phi inverse, from W to Rm, such that, so it's not going to be onto, right? So it's not a bijection, it's just one-to-one, such that the following 3 conditions hold. So firstly, phi inverse of W is equal to M intersect U. So basically W is playing the role of V intersect the subset Rn of Rm. D phi inverse has rank n for all x in W, so d phi inverse at the point x. And finally, there's a map phi, which goes from phi inverse of W to W, and it's continuous. So the proof that, one direction of the proof is that this characterization of a manifold is the same as this characterization. And going from the first, from the first definition to the second is fairly simple because you just set W to be V intersect of the set where yn plus 1 through ym are all 0, and psi inverse is just exactly be inverse restricted to this set. So, but to go the opposite direction, you should take a look at Spivak. We're not going to get into the details of this proof, but essentially, you can also characterize manifolds by basically parameterizations of the coordinate charts. Okay, so we're also, by sort of an abusive notation, we're also going to call these pairs psi w are also coordinate charts. This is kind of an abusive notation, but different authors actually call sort of things that go from with target the manifold coordinate charts, and then other authors will call things with domain the manifold coordinate charts. So it's not really settled in the literature. So for us, they're both coordinate charts. But we'll be clear about what the domain and the range is. So for example, psi inverse here should be the coordinate chart. Okay, so the final thing that we want to introduce in this video are manifolds with boundary, which are going to be crucial for Stokes' theorem. So before we do that, we need to define what the half space is. So what exactly we're modeling our manifolds with boundary on. So the half space, which we denote with a bold H, is the set of all x1. Let's actually put this down here. x1 through xn in Rn, such that xn is greater than or equal to 0. So we're going to use this to define our manifolds with boundary. So in these previous definitions here and here, I can't describe something like a disk or a ball as a manifold. It's because those things have this sort of edge. So a manifold with boundary is going to take that into account. So the definition of a manifold with boundary is very similar to that of a manifold. So I'll just remind you of it up here. And then I'll say a smooth n-dimensional manifold with boundary is M, which is a subset of Rm, with U and V as in the definition of a manifold, but we can either have, so instead of this condition, which I'll outline in pink, instead of this pink condition, so we can have the pink condition hold. So this condition that every point has a neighborhood U, which locally basically looks like Rn. So either the pink condition holds or a condition holds which basically says that the neighborhood U of P locally looks like the half space. So V of U intersect M is equal to V intersect the half space cross the point 0, 0, 0, which is just equal to V intersect all points in Rn or Rm where Yn is greater than or equal to 0 and Yn plus 1 is equal to 0, etc., all the way up to Yn equaling 0. And phi of P has Yn equal to 0. And the set of all, so I'll box this in green. And the set of all P in M where the green condition holds is called the boundary of M. And it's denoted by boundary of M. So as an example, let's consider the two disk. So the two disk is the set of all points x, y in R2 such that x squared plus y squared is less than or equal to 1. And for if x squared plus y squared is strictly less than 1, then we can have U just be some open set containing x, y, which is a subset of the interior of D. So basically, if x squared plus y squared is less than or equal to 1, then there's always some set U which is open, contains x, y, and doesn't intersect the boundary of the disk. But if x squared plus y squared is actually equal to 1, then we need to come up with a different type of coordinate chart. And I'm going to define, so instead of defining this coordinate chart using sort of directly using this condition, I'm going to use our alternate condition up here because it's easier when I'm using polar coordinates. So I'm going to define phi inverse of theta rho to be 1 minus rho cosine theta, 1 minus rho sine theta. And in this case, if I take the theta rho coordinate and I look at maybe this box here, so this is some, this is the intersection of a image of, for example, perhaps like the image of some set V with the upper half space. So that will be, so the set V will be in blue and the set V intersect the upper half space is in red. So the whole thing is V. Then if I look at V inverse, it's going to send this, it's going to send V intersect the upper half space. Well, it'll send V to something like this, and it'll send V intersect the upper half space to this part. And you can see that there's going to be a sharp line, which is the boundary. I'll actually draw that in green to make it more obvious. This is the boundary. Okay, so it's a way to make mathematically precise a concept of boundary that we sort of intuitively understand.